Imagine a future control room. No operators, no engineers monitoring screens, no human dispatchers, only algorithms, artificial intelligence forecasting load, AI detecting faults, AI isolating lines, AI restoring power, AI defending against cyber attacks, and no human pressing any button. At first glance, this sounds like progress. Faster decisions, no fatigue, no human error, no emotional bias. So here is the question. If AI is faster, more consistent, and capable of processing millions of variables per second, why not let it control the entire power grid? Why not remove humans completely? Today, we will explore why that idea, as tempting as it sounds, will find is dangerously incomplete. This is not an anti-AI argument, it is a pro-resilience argument. And when we talk about power systems, especially HVDC corridors, protection schemes, and national grids, resilience is everything. Artificial intelligence is already embedded in modern power systems. It is used for load forecasting, renewable output prediction, voltage stability assessment, fault classification, predictive maintenance, cyber intrusion detection, energy market optimization. In many cases, AI performs better than classical deterministic algorithms, so the progression feels natural, from assistance to supervision to autonomy. But here is the subtle shift. Using AI as a tool is fundamentally different from depending on AI as the ultimate authority. Power grids were historically designed around layered protection, primary protection, backup protection, redundant communication, independent operators, manual override capability. This architecture reflects a core philosophy. Never allow a single point of failure. Blind reliance on AI introduces something new, a single cognitive authority. And that is not how resilient systems are built. Let's define terms carefully. Blind reliance does not mean using AI. It means accepting AI decisions without validation, allowing irreversible actions without explainability, designing systems assuming AI is always correct. In protection engineering, every trip signal must be traceable, auditable, and explainable. If an HVDC converter blocks, engineers must know. Was it overcurrent? Was it harmonic instability? Was it commutation failure? Was it cyber manipulation? An AI system that outputs only confidence, 98% fault condition, is not sufficient. Power systems require reasoning, not just prediction. AI systems are fundamentally statistical. They learn from historical SCADA data, recorded disturbances, simulated contingencies, labeled fault datasets. But real power systems face rare cascading events, black swan failures, combined cyber-physical attacks, extreme weather beyond historical records, geopolitical disruptions. These events are, by definition, underrepresented in data. Consider the 2003 North American blackout, the 2012 India grid collapse, Texas winter storm, 2021. Many of these failures involved complex interactions that were not part of standard training datasets. AI models extrapolate, humans hypothesize. That difference matters when confronting the unprecedented. A human operator may say, "This pattern doesn't match anything I've seen. Let us isolate conservatively." An AI model may say, "Statistically acceptable," and act. Modern AI systems, especially deep neural networks, are often black boxes. They provide outputs, but not reasoning chains. In grid protection, this is unacceptable. Protection systems must be deterministic, auditable, defensible in court. If an AI-controlled relay trips a 2GW HVDC link incorrectly, the consequences are enormous. Economic losses, frequency deviation, cascading outages, political repercussions. Engineers must answer, why did it trip? If the answer is, the model weight vector triggered a non-linear activation, that is not operationally sufficient. Transparency is not optional in critical infrastructure, it is mandatory. AI does not only fail randomly, it can be attacked intentionally. Research has demonstrated false data, injection attacks, adversarial perturbations, data poisoning, model inversion attacks. Imagine a coordinated cyber attack injecting subtle measurement distortions into PMU streams. An AI stability monitor may misclassify the system state, trigger unnecessary load shedding, block HVDC links, or worse, ignore a real instability. Humans have intuition shaped by physical understanding. AI has probability distributions. Confidence is not the same as correctness. And adversarial systems exploit confidence. AI excels at optimization. But power systems are not purely economic systems. They are safety-critical systems with uncertainty. Optimization algorithms may reduce spinning reserve, tighten voltage margins, maximize line utilization. In stable conditions, this increases efficiency. In unstable conditions, it accelerates collapse. Cascading failures often propagate through tightly coupled optimized systems. Humans under uncertainty tend to increase safety margins. AI under optimization, objectives tends to increase efficiency. Resilience requires intentional inefficiency. That is a philosophical and engineering principle. If an AI-controlled system causes a national blackout, who is responsible? The developer? The utility? The regulator? The algorithm? AI cannot appear in court. It cannot explain intent. It cannot assume moral responsibility. Electricity is not social media. It is not advertising. It is national infrastructure. Legal systems today assume accountable human decision makers. Until governance frameworks evolve, full autonomy creates dangerous ambiguity. AI is often described as objective, but AI reflects training data, designer assumptions, optimization objectives. If the objective function prioritizes economic efficiency over social equity, AI will enforce that bias. Load shedding decisions are not purely technical. They involve hospitals, water systems, critical services, vulnerable communities. These are policy decisions. Policy must remain human-governed. The scientific consensus increasingly supports assisted intelligence, not replacement. 3 resilient architectures exist: human in the loop, human on the loop, AI supervised, human governed. This hybrid model combines machine speed, human reasoning, institutional accountability. The goal is not autonomous grids. The goal is intelligent grids with governance. Artificial intelligence will shape the future of power systems. It will enhance forecasting, improve stability assessment, strengthen cyber defense. But intelligence without wisdom is dangerous. In critical infrastructure, the greatest risk is not error. It is unaccountable error. Power grids require redundancy, transparency, ethics, human oversight. Because when the lights go out, society does not blame the algorithm. It looks for a human explanation. And that responsibility cannot be automated. Thanks for watching. Stay safe and stay curious.